Our first of these talks is going to be given by a scientist at TCL. His name is Yasar. He's going to be speaking to us about self-supervision in the context of video being used in a federated setting. So with that, I'm going to hand over to Yasar.
All right, cool. So let's get started. Hello, everyone. I'm Yasar. I'm a research scientist at TCL Research Hong Kong. Today, I'm going to present something about video self-supervised learning in the federated setting. It's a joint work between TCL Research Hong Kong and University of Cambridge. As you can see in the title, there are two important terms in this slides. One is video self-supervised learning, and the second is the federated settings. So let's first talk about what is video self-supervised learning. When we talk about self-supervised learning, self-supervised learning is a method which contains two tasks. The first one is the pretext task, and the second is the downstream task. In the pretext task, we learn some feature representations from the data, and we hope that these feature representations could be helpful for us to improve our performance on the downstream task. And that downstream task could be anything. In terms of video, it could be action recognition, or it could be video retrieval. So as you can see, a pretext task play an important role in self-supervised learning. There are two things that we need to keep in mind while designing a self-supervised learning pretext task. The first thing is that it should be independent of the data distribution, the actual class distribution. And the second thing is that these supervisory signals or pretext tasks should be generated in an automated way. So there are different ways to generate these supervisory signals. So for example, as you can see on the left side of this video, we can basically shuffle the clips of the video, and we can ask the network to predict the order of these shuffled clips. We can also have a video being played at normal speed and a video being sped up, and we can ask the network to predict whether this video is being sped up or it's played at the normal speed. Or we can also design a pretext task where we basically superimpose the synthetic patches on top of the video at certain locations, and we can ask the network to predict the location of those synthetic patches. As you can see, and as I mentioned before, in this self-supervised learning task, the supervisory signal should be generated in an automated way, and it should be independent of the labels. When we combine this pretext task or we deploy this pretext task in a federated setting, there are obvious two advantages we can have. Normally, these pretext tasks are like self-supervised learning is being done in a centralized way, and we all know that what are the limitations when we do training in a centralized way. One of them is obviously the data privacy, and also the other thing is that when we do training in a centralized way, the performance of the model is limited to the data only available at the centralized centers, and that basically limit the performance of this self-supervised learning, and also basically limit the capabilities of these self-supervised learning method. Otherwise, if we have access to the large-scale uncurated real-world data set, we can get more out of these self-supervised representation learning method. So in this spirit, we designed a federated self-supervised learning framework by integrating Flower with MMCB. And this Flower framework actually allow us to deploy these self-supervised pre-training tasks on around 100 clients. There are obvious advantages. As I mentioned before, we can get rid of the actual class labels. And this is quite interesting because normally in the federated settings, you might have seen that we do label-based training. And now here, with the introduction of self-supervised learning, we don't really care about the labels, what labels are present in the data. We only care about what properties we can learn from these data. And later on, when we perform these federated learning, like after pre-training in a federated learning way, we can use these learned representation for the downstream task. So other aspect is that we can do that in a privacy preserving manner. There will be less data storage requirement at the server, so cost saving. And also we can have access to a large uncurated real world data set, so we can learn some better real world representation. And we did some experiments with MMCV and Flower, and we found some quite interesting results. So this is our preliminary results and with very interesting observations. So the first observation we found is that the fine-tuning performance degrade with the FL pre-training, as we already know, because we are doing a distributed training and we can't really make sure that we can get really par with the fine-tuning performance with FL pre-training. But the good thing is that with the linear probe, in which we only learn the representation, and we then take those representation, and on top of those representation, we actually use a classification head to train it for our intended downstream task. We got mixed results, and we see that for some federated learning pretext tasks, we got better results, where for the other, we got worse results. Interesting thing is that when we took those representation and we perform video retrieval, in which case we don't really need any training, we found that for most of these pretext tasks, we got better retrieval performance for the CTP and speed, which are two of the self-supervised learning approach. And this is quite surprising. To further analyze why we are getting such good results for video retrieval, we analyze the loss landscape of the centralized pre-training and the federated pre-training. And we found that when we do federated pre-training, we basically get a really wider loss surface. And it has been shown that if you have a wider loss surface or wider minima, then you can achieve better performance. And that perhaps explain or answer a little bit about why the video clip retrieval performance is better. The other interesting thing is that when we have IID and non-IID data distribution based on the actual class labels, with FL pre-training, we get similar performance with IID and non-IID. And that basically is quite interesting, because normally in the federated learning, you deal with the labeled data set, and that automatically induce the notion of heterogeneity. But with the federated pre-training, assuming that all of the clients are running the same self-supervised learning pretext task, we can get rid of, we don't really need to take care about whether the data is IID or non-IID, because at the end, we are not learning something based on the labels, but we are learning something based on the properties of the data. So with this, I'll conclude this presentation. So in the conclusion, I can say that federated self-supervised learning is possible, not only for videos, but also for images. And in fact, there are a lot of, there are a few examples of federated self-supervised learning for image-based datasets. We propose a FedVSSL Flower FedVSSL framework built on top of Flower, integrated with MMCV. Time is quite limited, so it would require like a 1 or 2 hour session to cover this up. So once we integrate Flower with the MMCV framework, we build a generalized framework that we hope that we can not only be used for video SSL, but also for image-based SSL as well. So with that, thank you very much for listening to me, and I'm open to questions.
Great. Thanks for this work. It's really fantastic stuff.